Hi everyone, this is the Hungry Math Professor here. Welcome to my channel. Today we're going to be discussing um, Prime Obsession by John Derbyshire. And this is a fantastic book. It was published in 2003 and it won the Mathematical Association of America's inaugural Euler Book Prize in 2007. And it tells the story of, the secondary title here is Bernard Riemann and the Greatest Unsolved Problem in Mathematics. So Bernard Riemann is a mathematician. He lived from 1826 to 1866. And interesting enough, my research area is Riemannian geometry or geometric analysis. So Riemann had a huge effect on the area of math that I work in. But what's interesting is that he also had a huge effect on lots of different areas. And this book is really nothing about Riemannian geometry or geometric analysis. Instead, it's related to number theory. And the way the book is written, every even number chapter tells about the history. So you learn about various different mathematicians that built up to um, what's going on here. And the odd number chapters then fill in some mathematical details. So that already is a very interesting way of writing this book, right? You go back and forth between history of the problem and learning about these different characters and biography, and then every other chapter you get some mathematical details. Now that being said, the math is presented fairly well, but this is not easy mathematics to present. So you're going to have to work a little bit in those math chapters to understand, especially depending on what your math background is. You just can't expect to learn some difficult, interesting, insightful mathematics without having to do a little bit of work. So, be prepared for that if you're going to read this book. But I would say, it's up to you what level you want to get into, right? Everyone can read the historical chapters and really enjoy the story going on there. And then in the mathematical chapters, you may want to just get the big idea, and you just don't need to, you know, plow through and understand every single detail. That's kind of up to you. But what is this book about? Well, it's about the Riemann hypothesis, which is this famous unsolved problem. It was on Hilbert's list of problems, but it's also now a Millennium Prize problem, which means that if you solve it, you would get $1 million prize. And um, there's only been one Millennium Prize problem which has been solved, and that's the Poincare conjecture by Gregory Perelman. And that problem is actually related to my area of research. The method that was used to solve it is called Ricci flow, and that is a type of geometric evolution equation which uses Riemannian geometry. But the rest of the Millennium Prize problems have not been solved, and one of them is the Riemann hypothesis, which is what we're aiming to study here. Now, if you look at the Riemann hypothesis, it's a statement about the zeros of a particular complex function. Complex function means the range and the domain. The domain and range are both the complex numbers. And it tells you something about where the zeros of this function should live. And this function is called the Riemann zeta function after Riemann. But then you're told, you're always told that the zeros of the Riemann zeta function are related to the distribution of the prime numbers, right? Because if you see this Riemann zeta function and you hear that $1 million prize is attached to it, your first question is going to be, why is this function so important? Because it's not clear from the statement of the problem that this function is really interesting at all. Like it just seems like a question that someone in complex analysis would be interested in, but not something, that you put on a list of seven problems that have $1 million prize associated. But the key to that is that it's always said that it's related to the distribution of prime numbers. And so then there's a natural question. If you have even an inkling of curiosity in your bones, you're going to ask, how? How is it related, right? And you might think, oh, maybe there's just like a little equation they have to write on the board, and it'll, easily go from the zeros of this complex function to something about the prime numbers. And that's not quite true. So it's not so easy to explain the link between the Riemann zeta function and the zeros of the Riemann zeta function and the distribution of the prime numbers. So the object of this book, one of the goals of this book is to show you that link. And so I really enjoy this because I didn't know what that link was. I don't work in number theory. I don't work in complex analysis or analytic number theory. So I hadn't really, I'd only heard of this, that this was the case, but I had no clue how. I always suspected maybe there was one or two equations, but it turns out it's much more in depth than that. And so it's a really great book in that sense that it gets you that goal of understanding a little bit of how the Riemann hypothesis is related to the distribution of primes. Now, to tell this story a little bit more detail, let me go back for a second, right? So, first of all, if you're studying the natural numbers, so one, two, three, four, five, so on and so forth, you start noticing that there are these prime numbers, right, that cannot be broken down any further. So, like 2, 3, 5, 7, you can't break these down, 11, 13. You don't break them down into smaller factors, right? So we call them prime. So the first question you might ask is, are there infinitely many primes, right? Because it's possible that maybe you get up to large enough numbers and they're always, you always can break them down into smaller pieces, right? But it turns out that that's not the case. There are infinitely many prime numbers. This was proven a while ago. It occurs in Euclid's Elements, the proof, and it's basically the same proof that I teach my students. I think I'll do a video going through this proof because it's a fairly simple proof. It's a pretty proof, and it's a nice fundamental result about prime numbers. So there are infinitely many prime numbers. Not only that, we have the fundamental theorem of arithmetic, which says that any number, any natural number, can be broken down into a product of primes in a unique way up to sort of permutations. So, for instance, 10 can be written as 2 times 5, right? Okay, so that means that the prime numbers are somehow like the raw material of the natural numbers. Like everything can be built up out of the prime numbers, right? In some unique way up to permutation. So that's the fundamental theorem of arithmetic. Okay, so if the prime numbers are the raw material, then they are really important to study, and understanding the prime numbers is really, really interesting. And if you start thinking about it, one of the intuitions I mentioned earlier is still sort of true. As you get larger and larger numbers, you do expect there to be sort of less primes. I'm not going to be too specific about that, but basically, the larger the numbers get, you expect that it's more likely that they can break down into smaller pieces. Is the rough idea, and there's something to that. So the next question becomes like, what is the distribution of these prime numbers? Like how sparse do they get? How much are how many are there? Can we be very specific about like in a certain range how many prime numbers there are, things like that. And of course, there's this twin prime conjecture because we noticed that there's a lot of these twin primes like 11 and 13 that differ by 2, and 11 and 13 differ by 2. And you might wonder, like, are there infinitely many of these twin primes? Which is kind of interesting because, again, this intuition that the primes sort of spread out. If there's infinitely many twin primes, then although maybe in general they spread out, there's still sort of these twins every so often. So there's lots of interesting questions about the prime numbers, and there's lots of them that are not solved. But for instance, one of the other ones that comes up in this book is the prime number theorem, which is sort of a good attempt at giving us some idea of the distribution of the primes. And what the prime number theorem says, let's say you fix a number n, which you think of as like a really big number, capital N, which represents like, I want to know how many prime numbers are there less than that number, capital N. And the prime number theorem says that it's approximately capital N divided by log of n. So if the answer was capital N, then that would say basically almost every number is prime. And we know that's not the case. But instead, the prime number theorem says it's capital N divided by log n. So that gives you a rough idea of how many primes you should expect and gives you some good sense of the asymptotics of how many primes there are. But again, you still want to go deeper. You want to have a deeper understanding. And, the whole area of analytic number theory studies this. So there's lots of other results that I'm not even aware of. But the book covers some of the big ones, like the prime number theorem. But the sort of big unopen, the big open one is the Riemann hypothesis. And I'll let you read the book to get more details because I can't explain everything in this video, but it's a really pretty ride through this book. again, at the very least, you'll love the historical chapters. I think you'll understand most of the mathematical chapters, and you'll get a good idea of what's going on with this problem. So check it out. Let me know what you think. Like, comment, and subscribe, and I hope to see you at another video.